Math 2414, volumes, shells, motivation for a new technique. A little underdressed today. In the previous series of videos, we talked about volumes, but the way we talked about them was to look at a cross-section of a solid when we sliced it in a cut perpendicular to the axis of rotation. And we looked at that cross-section and said, what's the area of this cross-section based on where I cut this solid? And then we just integrated that area. Now, most of them that we did were solids of revolution, where we took a lamina and rotated it around an axis. And as a consequence, when we cut that solid and looked at the cross-section, it was always a circle. Now, sometimes it was a washer. For example, if we had some little lamina up here and we rotated it around the x-axis, then this gap in between when we spun it would create a hole in the middle of the disc, and we had to figure out the outer radius and the inner radius, and then the outer radius we squared and multiplied by pi for the area of the big circle, and then the inner radius we squared and multiplied by pi and subtracted because that was the area of the circle we took out to make the washer, and then we integrated that. But unfortunately, that plan of attack won't always work. This first example will show you why, and it will motivate the need for another way to calculate the volume of a solid of revolution. In this example, we're going to find the volume of the solid obtained by revolving the following lamina around the y-axis. This lamina is bounded above by the equation y equals 2x squared minus x cubed, and bounded below by the x-axis. Now, before we go any further, let's go ahead and figure out what the x values are that where the curve intersects the x-intercepts, if you will. And finding those intersection points is pretty easy because the equation of the x-axis is y equals 0, so we just have to put in 0 for the y and see what we get. 0 equals 2x squared minus x cubed. This is an easy factoring situation. We can just factor out an x squared. That would leave 2 minus x. And then, since the product is equal to 0, we can set each factor equal to 0. X squared equals 0, and 2 minus x is equal to 0, giving us x equals 0 and x equals 2. So now we know exactly where this guy hits the x-axis. That's 0 and a 2. But here's the problem. If we try to do this using discs or washers, in this case it would be a washer. Remember that you can tell when it's going to be a disc method or washer method based on whether or not the axis of rotation is a boundary on your lamina. If we were going around the x-axis, then yes, we could use the disc method because the axis of rotation is a boundary on this lamina. But since we're going around the y-axis, which is not a boundary of this lamina, we can't use the disc method, so we have to think about it as from the washer method. So if we spin this thing around and we want to do the washer method, we have to take a cross-sectional cut perpendicular to the axis of rotation. And since our axis of rotation is the vertical y-axis, our cut would be horizontal. Now, why is this a problem? Because when we do the washer method, we have to find an expression for the outer radius and the inner radius. And then we would integrate pi big R squared minus pi little r squared. But this would be a dy integral. How can you tell? Because this cut has a very narrow y dimension. In other words, yeah, this is some x value. Actually, the x value would be here. But the skinny dimension, the one that we let go to 0 in the Riemann sum, if you will, is in the y direction. In other words, this is a delta y, very small change in y, and that would become the dy, we'd be doing a dy integral. So what's the problem? Well, the problem with that is we would need to know this equation as a function of y, not a function of x. Because if we're going to integrate with respect to y, we need x equals, not y equals. Good luck solving this for x. It's not impossible. It's just a cubic equation. There is a cubic formula. And if you're thinking, we already did that, no. we solved this equation for x that had a 0, which made it very easy to solve. But with a y over here, solving for x is difficult. You want to know how difficult? Search cubic formula, which is like the third degree equivalent of the quadratic formula, and you'll understand why we don't use it. So we've kind of reached an impasse in that there's no way we're going to be able to solve this equation easily for x, so that it says x equals a function of y, and then that function of y will play its role over here. So the washer method is failing us now because we chose to, well, we didn't choose, we took a cross-sectional cut perpendicular to the axis of rotation, forcing it to be a dy integral, but this isn't a function of y, this is a function of x. Does that mean we can't do this problem? No, it just means we can't do it that way. So how can we do it then, if we can't do it using a cross-section, a cut that is perpendicular to the axis of rotation? Well, maybe we need to cut this differently. Instead of cutting this lamina, or really when I say cut it, I mean cut the solid, we spin this thing around, it would look like a donut with a hole didn't quite go through. If we spun this around, we could think about taking a cross-section, a cut perpendicular to the axis of rotation. Well, what if we took a cut parallel to the axis of rotation and spun that around? Maybe we can do something with that. Well, in the next video, we're going to develop and utilize this new technique, which will be called the shell method.